For this example, we are trying to find the center, the radius, and the intercepts of the circle with the given equation, and then sketch the graph. So we are given the equation of a circle. That equation is x squared plus y squared plus 2x minus 8y plus 1 equals 0. This is a format for the equation of the circle that we call general form, or you might think of it as an expanded form. So this is general form. A general form is not the most convenient form for us for what we're doing. Because we're looking for the center and the radius, it's much nicer for us to have it in the standard form. The standard form is x minus h squared plus y minus k squared equals r squared. The ordered pair HK is the center of the circle and R is the radius. So if the equation was written in standard form, we would easily be able to answer these first two parts of the question. So what we're going to do is we're going to use something called completing the square to rewrite the equation from general form and turn it into standard form. So here's the process that we'll go through. What we want to do is group the x terms together. So we want to group the x squared and the 2x together. We have x squared plus 2x grouped together. We want to group the y terms together. So we'll group y squared minus 8y together. And we want to move the constant term to the other side. So we do that by subtracting 1 on both sides. And now our constant term is on the other side. So then we're going to make some space in the x group for another term and make some space in the y group for another term. And these terms that we want to add to the group are going to complete the square. They're going to make it so we get these perfect squares that you see. These perfect squares that you see over here. So we want to choose the right number. I typically call this number the magic number. We're going to find the magic number for the x's. And to get the magic number for the x's, you want to start with the coefficient of the x term. So you start with that number, and you're going to cut it in half and square it. So 2 divided by 2 is 1. 1 squared is 1. So the magic number for the x group is 1. Now let's find the magic number for the y group. So we follow the same procedure. We start with the coefficient of the y term. So we're going to start with that -8. We cut it in half and square it. So -8 divided by 2 is -4. -4 squared is 16. So we found the magic number for both the x group and the y group. Now we want to add those numbers to the group. But with equations, you can't just add whatever you want. You have to balance the equation. So whatever we do to one side of the equation, we do the same thing to the other side. So I want to add a 1. That's the magic number for the x group. And I have to do the same thing on the other side of the equation. I want to add a 16 to the y group. To balance, I add a 16 to the other side of the equation. And now each one of those groups is going to factor into a perfect square. So x squared plus 2x plus 1 is a trinomial. I'm going to factor it to two binomials. And x times x gives me the first term of x squared. 1 times 1 gives me the last term of 1. And if we multiply the outside and the inside, that's x and x. X plus x will give me the 2x in the middle. So I just need these to be positive. So when we factor that trinomial, you'll see both binomials are the same, and so we can write that as a square. X plus 1 times x plus 1 is x plus 1 squared. For the y group, we have a trinomial, and we want to factor it into binomials. Y times y will give me the first term of y squared. 4 times 4 gives me the last term of 16. The inside and the outside are 4y and 4y. We need it to make a negative 8y in the middle. So we'll make these both negatives. Negative 4y plus negative 4y is negative 8y. So we factored that trinomial. It became y minus 4 times y minus 4. We can write that as a perfect square. Y minus 4 squared. On the right-hand side, we're going to combine those like terms. Negative 1 plus 16 is 16. And so now we've written that equation in standard form. And now that it's in standard form, we can identify the center. The center will be negative 1, 4. That's the HK. And the radius will be 4. The square root of 16 is 4. Now we also want to find the intercepts of our circle. Now you can find the intercepts using general form, or you can find the intercepts using standard form. How about we do this? I will find the intercepts. We want to find the x-intercept and the y-intercept. So I'll find the x-intercept using general form, but I'll use the y-intercept using standard form, just so you can see a variety of ways to do it. So let's start with this general form. X squared plus y squared plus 2x minus 8y plus 1 equals 0. And I'm trying to find the x-intercept. To find an x-intercept, you let y equal 0. I'll substitute a 0 in for y. That's x squared plus 0 squared plus 2x minus 8 times 0 plus 1 equals 0. We'll simplify and get x squared plus 2x plus 1 equals 0. And let's see if I can factor this. X times x is x squared, the first term. 1 times 1 is the last term. And we can do both pluses to get the middle term of 2x. And I can set each one of these factors equal to 0 and get x equals negative 1. So we only have one x-intercept, and that's going to be negative 1, 0. Then I'll find my y-intercept using the standard form. x plus 1 squared plus y minus 4 squared equals 16. So remember, these two equations are the same equation, just a different formats. So you can use either one of them to find the intercepts. So we're going to look for the y-intercept. And you find a y-intercept by letting x equal 0. That will give 0 plus 1 squared plus y minus 4 squared equals 16. 0 plus 1 is 1. 1 squared is 1. So we have 1 plus y minus 4 squared equals 16. And I'm going to solve for y by subtracting 1 on both sides. That gives y minus 4 squared equals 15. I'm going to get rid of the square by square rooting both sides. The square root and the square cancel each other out, and I get that plus or minus symbol on the other side. Sorry, I changed that 15 to a 16, so it should be 15. And I'll add 4 to both sides. So I have y equals 4 plus or minus the square root of 15. And that means I've got two y-intercepts. Got a y-intercept of 4. Let me write it as an ordered pair. 0, 4 plus square root of 15. 0, 4 minus square root of 15. So we've got our center, radius, intercepts. One last thing that we want to do is to graph our circle. We know that the circle has a center of negative 1, 4, and a radius of 4. So I'm going to plot that center of negative 1 and 4. And we want to move the amount of the radius away from that circle. So I'm going to go to the right 4, down 4, to the left 4, and up 4. And we can sketch out the circle. So what's nice here is that this confirms the work that we did earlier. You can see one x-intercept, the circle just touches the x-axis here. And you can see two y-intercepts. So let me zoom out so you can see all the work that we did. So we started off with an equation in general form, the general form of a circle. We used completing the square to turn it into standard form of a circle. And once it was in standard form, we were able to identify the center and the radius of the circle. Then we looked for the intercepts, and we found the x-intercept by letting y equal 0, the y-intercept by letting x equal 0. And I showed you using both formats how you could find the intercepts. And then we graphed the circle using the center and the radius. Okay, so I'm going to give just a brief overview about finding domain related to this test that we're working on. You're going to be asked to find the domain of these different types of functions: polynomial, rational, root, and there are two types of root: root with an even index, root with an odd index. So when you're asked to find domain in this chapter, what you want to do is figure out which category your function fits into. We're not going to go into a lot of detail about these definitions, but the basics are that when you see a variable in the denominator, that's when you're talking about a rational function. When you see a variable inside of a radical is when you're talking about a root function. And then the index is right here on the root. And so you want to pay attention to whether that index is even or odd. A square root will be even, a cube root will be odd index. And then pretty much everything else will fall into the polynomial category. So these are the types that you're going to get tested on for test 1. We'll add more later on in the class. We'll add more types of functions. So I pulled this handout from my website, which gives a summary of how to find domain for each one of these categories. So when you have a polynomial function, you have no restrictions on the domain, and the domain will be all real numbers, negative infinity to infinity. When you have a rational function, because you have a variable in the denominator, that denominator can't be 0. You will have a restriction. So that denominator, your denominator is q of x, your denominator equaling 0 is going to be a restriction. So you solve that equation, and then you exclude those values from the domain. Now, when you have a root with an even index, like a square root, you have restrictions. For example, square root of -1 gives you I, the imaginary unit. And we're only looking for when we get real numbers, not imaginary or complex numbers. So we have a restriction that the numbers underneath the radical need to be positive or greater than 0. So that's going to be our restriction for even index roots. For odd index roots, there's no restriction. So no restriction means the domain will be all real numbers. So on this same handout from my website, I have a bunch of different examples here. And looking at these examples, you can see that all of these have variables in the denominator, so they are rational. All of these have roots with an even index. All of these have roots with an odd index. And here, we don't have a variable in the denominator. We don't have a variable inside of a radical. So we have polynomials. So all of these, 1, 2, and 3, will have a domain of all real numbers. All of these, 10, 11, 12, have a domain of all real numbers. Remember, we said polynomials have no restrictions, and roots with an odd index have no restrictions. But rational functions have restrictions, and roots with even index have restrictions. So I'm just going to take one of these. Let's take this one because it looks the most complicated. And I want to find the domain of this rational function. So remember, rational functions have a variable in the denominator. That denominator cannot equal 0 because that's undefined. So what we do to figure out what our restriction is we say, well, what if that denominator equals 0? And we figure out what the restrictions are for this particular example. So we've got x cubed minus 2x squared minus 15x equals 0. I'm going to solve that equation. So first factor out the x that's in common. We get x times x squared minus 2x minus 15 equals 0. Then let's factor the x squared minus 2x minus 15. We get x and x. 15 could be 5 times 3. And we need a minus and a plus to create that middle term of 2x. And then we're going to set each one of those equal to 0, each factor equal to 0. And we get x equals 0, x equals 5, x equals negative 3. These values of x will cause the denominator to equal 0. So these are our restricted values, and we need to exclude them from the domain. So on our number line, we have all real numbers from negative infinity to infinity. And we're going to exclude negative 3, we're going to exclude 0, and we're going to exclude 5. But we're going to include all these numbers that are less than negative 3. So we can write that in interval notation. Negative infinity to negative 3. These are all the numbers that are less than negative 3. We want to include all of these numbers between negative 3 and 0. So we want to include negative 3 to 0. We want to include these numbers in between 0 and 5. So we write the interval from 0 to 5. And we want to include these numbers that are greater than 5, from 5 to infinity. So this is our domain of the rational function q of x equals x over x cubed minus 2x squared minus 15x. So let's do an example of an even root. Even though this one looks more complicated, we don't do this one in our class. In my pre-calc class, we do problems like that. So let's do this one here. And this is a root function with an even index. The index is 4. You have g of x equals the 4th root of 5 minus x. So that is an even index root. And even index roots have restrictions. We want what's underneath the radical to be positive or equal to 0, because the even root of a negative would give you a complex number. We only want real numbers. So we're going to take the expression underneath the radical, and we want that to be positive or equal to 0, greater than 0 is positive, and equal to 0, and we solve that inequality. We're going to subtract 5 on both sides. This is negative x is greater than or equal to negative 5. We're going to divide both sides by negative 1. When we divide an inequality with a negative, we reverse the inequality. We have x is less than or equal to 5. So on our number line, we're including 5, and we're including everything less than 5. So to write that in interval notation, we would have negative infinity to 5 with a bracket to include that 5. So hopefully, let me zoom out so you can see all these examples. I've given you an overview of the different types of domain questions that will show up on the test. So you've got to first categorize and then find the domain for that category. Polynomials are the nice ones. They will have x to a whole number power. There are no restrictions, and you say the domain is all real numbers, negative infinity to infinity. Rational will have a variable in the denominator. You can see there's a variable in the denominator of each one of these examples. To find the domain, you set the denominator equal to 0 and solve. These are your restricted values, and you exclude those values from your set of all real numbers. Then you have even roots. So you'll see your radical, and then you look at the index. The index should be an even number. And to find the domain, you would set the expression underneath the radical greater than or equal to 0 and solve. When you solve that inequality, you'll get the domain. If you have a root with an odd index, here we have the cube root, the 5th root, the 7th root. These do not have any restrictions on the domain, and so the domain is all real numbers. For this question, we want to know for what values of x does the function obtain a relative minimum. Find the relative minimum value. For what value or values of x does the function obtain a relative maximum? And we want to find that relative maximum value. So in our book, the way that a relative minimum is defined is noticing a change from decreasing to increasing. So if we look at our graph and find a change from decreasing to increasing, that's going to create a minimum value. And in our book, the definition of relative maximum is when we have a change from increasing to decreasing. So a change from increasing to decreasing is going to create that relative maximum. So first we want to analyze the graph for increasing and decreasing, and then we'll see if there are any changes. And if we notice changes, then we have a relative minimum or maximum value. So I'm going to trace the graph going from left to right. So this point here is the farthest left, this ordered pair -12, -11. It's the farthest left. And I'll start tracing the graph, and as I'm tracing the graph, I notice that the y values are increasing. So this portion of the graph is increasing. And when we get to -8, 5, we can now see that the graph is decreasing. And then we get to this point here, -2, -4, and it's now increasing, and it stops at 1, -1. So we can see that this section of the graph from -12, -11 to -8, 5 is increasing. And then this section from negative 8, 5 to negative 2, negative 4 is decreasing. And the section from negative 2, negative 4 to 1, negative 1 is increasing. So we do have a change right here from decreasing to increasing, and it's at the ordered pair, negative 2, negative 4. So that point is a relative minimum point. Now, these two parts are asking about a relative minimum. So pay close attention here. The first part, part A, says what values of x? What values of x? So for part A, we're going to answer negative 2, the x coordinate. For what values of x does the function obtain a relative minimum? And then part B says find the relative minimum value. The minimum value is the y part, so that's negative 4. For parts C and D, we're looking for relative maximum. And we can see here is a change from increasing to decreasing at this point, negative 8, 5. And in part C, it's asking for what values of x. So that would be the x coordinate of negative 8. And for part D, find the relative maximum value. That's the y value. The maximum value is 5. On this example, we want to find the x-intercepts of the graph without graphing the function. We have our function being f of x equals the square root of x plus 3 minus the square root of x minus 1. And we're looking for the x-intercepts. And we can find the x-intercept by letting y equal 0. Now this is written in function notation, so you don't see a y. But we have to remember that f of x is the same thing as y. So we're going to find the x-intercept by letting f of x equal 0. And if we do that, that would give us the equation 0 equals x square root of x plus 3 minus square root of x minus 1. And we want to solve this equation. Now this equation is a radical equation or a root equation. And when you have radicals or roots, the strategy is to eliminate them from the equation first. So before you're able to solve the equation, before you're able to solve the equation with roots, you have to get rid of those roots. So that's our first step. So what we do is isolate one of the roots, and we're going to eliminate the root with the opposite operation. And then we're going to have to go through that process again. We have to go through it twice because there are multiple radicals in this problem. So I'm going to isolate the square root of x plus 3. So let's add square root of x on both sides. Let's add 1 on both sides. And that gives square root of x plus 3 on the right and square root of x plus 1 on the left. So now that I've got that radical isolated on one side, I'm going to do the opposite operation to get rid of it. the opposite of square root is squaring. And whatever I do on one side, I'm going to do the same thing on the other side. So I'm going to square the left-hand side. On the right side, the square root and square are going to cancel because they're opposite operations. But on the left-hand side, we're not able to cancel out that square root because of this plus 1 here. So we have to actually multiply this side out. Square root of x plus 1 times square root of x plus 1. Let's continue up here. If we multiply that out, we would have square root x times square root x plus square root x plus square root x plus 1 equals x plus 3. Square root x times square root x is square root x squared. Square root x plus square root x is 2 square root x plus 1 equals x plus 3. So on this right here, this is a 1 and this is a 1. 1 plus 1 gives us a 2. Square root of x squared is x. The square root and the square cancel. And you can see, just like I said, we were able to eliminate this square root by squaring both sides, but we still have the other square root in the problem. So we have to repeat the process over again. We want to isolate that radical and then eliminate it by squaring both sides. I'm going to subtract 1 on both sides, subtract x on both sides. That gives 2 square root x equals 2. Divide both sides by 2. We have square root x equals 1. Now I've isolated that radical, and I'll square both sides to get rid of it. And the square root and the square cancel each other out, and 1 squared is 1. So we get the x-intercept to be 1, but we need to check our work. Anytime we solve radical equations like this, by squaring both sides, you should always check, because you could get extraneous solutions. Extraneous solutions means extra solutions that don't work in the original equation. So I'm going to check this solution in the original equation, and that would be 0 equals square root of 1 plus 3 minus square root of 1 minus 1. This is square root of 4. Square root of 1 is 1. And we have square root of 4 is 2. Negative 1 plus negative 1 is negative 2. So we have 2 minus 2 is 0. So that does check out. So we do have our intercept being the ordered pair 1, 0. For this example, we want to find the equation of a vertical line through -2, -3. Now, for this one, finding the equation of the line can be a little bit challenging because a vertical line is different from all of the other lines. And the reason why it's different is that a vertical line has a slope that is undefined. The slope of a horizontal line is 0, and then if you have any lines that are tilted at all, you'll have a slope with some particular number. And so for all of the other examples where it asks you to find an equation, you have your formulas. Y minus y1 equals m times x minus x1, and you can substitute your slope in for m and work out what the line is. But for vertical lines have undefined slope, so we don't have a number that we can plug in for m to find the equation. So we have to know some facts about vertical lines to do a question like this. So what you need to know about vertical lines is that the equation will look like this. X equals some number. So the equation of every vertical line can be written in that format. Now, what number for our example? We're going to use the x-coordinate. X equals -2. That's the equation of a vertical line that's going to pass through the point -2, -3. Let's see a picture of that. So we want our line to pass through the point -2, -3. So -2 and -3 is right here. And we want it to be a vertical line that goes through that point. This is a vertical line, straight up and down. And you'll notice that every ordered pair on this line will have an x of -2. So that's why our equation is x equals -2. Every ordered pair on that vertical line has that same x-coordinate. So on this question, we want to find the domain and range using this picture. And this picture can be a little bit confusing because of all the dashed lines and the way that the lines curve around a lot. But what you should know is that these dashed lines are a special feature. We haven't studied yet, but we're going to study them in detail in a later chapter. These features of the graph are called asymptotes. And what you need to know about these asymptotes is that they're almost like fences trapping the graph. So if we look at just one of these, so let's look right here. You see the dashed line is y equals 5, and then you have your red line, which is the graph. The red line, which is the graph, is getting closer to the dashed line of y equals 5. So the graph is getting closer to the asymptote, and it never reaches it. It gets closer and closer and never reaches it. So on all of these sections here, where we have the graph close to the dashed line, these are all places where the graph is getting close to the asymptote but never reaching it. So that's going to be helpful for us in finding the domain. So when we're finding domain on a graph, what I like to do is to have a ruler or a pencil and hold it vertically. And the reason I'm holding it vertically is because when I hold it vertically, it's going along the x-axis from -infinity to infinity, and it's helping me see where my graph is, where the graph starts in terms of x's and where my graph stops in terms of x's. So this arrow that I see on the left is telling me that my domain is going to start at negative infinity. So I'm going to go from left. I start on the left because that's the smallest. And I'm going to go to the right and see where my graph starts and where it stops. So right here at the asymptote is a place where the graph stops. So remember what I said, this arrow, the graph is getting closer to the asymptote and will never reach it. So the graph does not exist at that asymptote. So that asymptote is happening, it looks like, at 2. So that's where my domain stops. But on the other side of the asymptote, the graph starts again. So I need to start up my domain again. And I apologize, it's a -2, not a +2. So these are both -2. The graph starts again and stops when we get to the next asymptote, which is 2. Then my graph starts again at 2 and goes all the way to infinity. So we get that our domain is from negative infinity to -2, -2 to 2, and 2 to infinity. So just to think of that in another way, here's your x-axis. Your x-axis is from negative infinity to infinity, and that whole x-axis is part of your domain except at those 2 asymptotes. You're just excluding those 2 numbers from the domain. So it's all real numbers except -2 and +2. Okay, so finding the range, we're holding the ruler or pencil horizontally because that points to your y scale. And we're going to go from bottom to top, that's smallest to largest. And this is going to help me figure out where my graph is. So you can see that I'm touching the graph down here. These arrows mean it's going to go on forever down. So my range is going to start at negative infinity. And as long as my ruler or pencil touches the graph, then I have parts of my range. So when we get up here, that's where my range stops because the graph stops right at the peak of that. So that is a y of 0. And I'm going to include that y of 0 in my range. You can see if I keep going up, I'm going to start having my graph again right at that asymptote. So the range will start at 4 and continue on to infinity. As I said earlier, the graph never reaches that asymptote, so I'm going to put a parenthesis on the 4. The parenthesis means that the 4 is not included in the range. So looking at our range values, we have y values from negative infinity all the way up to 0, and then we have y values again from 4 to infinity. So we found the range to be negative infinity to 0, including 0, union with 4 to infinity, not including 4. So On this question, we want to determine whether the function is even, odd, or neither. And we're given a picture of a function. And so we need to know graphically what even and odd mean. Even graphically means that our function will have y-axis symmetry. And odd graphically will mean that we'll have origin symmetry. So looking at this picture, we want to determine whether the graph has origin symmetry or y-axis symmetry. And if it does, then we can label it as even or odd. And if it doesn't have either of those types of symmetry, we're going to say neither even nor odd. So y-axis symmetry is when we have a mirror image over the y-axis. So that y-axis is the vertical axis, and you want to look to the left of the y-axis and the right of the y-axis to see if you have a mirror image. You could imagine that this is a piece of paper, and you fold that piece of paper along the y-axis, and you're looking for the two sides of the picture to match up exactly. And you can see that that's not going to happen with this picture. You have this piece that's up here. If you were to fold along the y-axis, you would need a piece of the graph on the other side as well. And we don't have that. So this particular graph does not have y-axis symmetry, which means that it is not an even function. Then we want to look at origin symmetry. Now the origin is this point here where the x-axis and the y-axis cross each other. And when you have origin symmetry, you are going to have symmetry in the opposite quadrant. So you're looking for in quadrant 1 to have a mirror in quadrant 3. So you're looking in these opposite quadrants over the origin to see if you have a mirror image. You also want to look in quadrant 2 to see if you have a mirror image in quadrant 4. So you're looking in those opposite quadrants. If we look at this picture, you can see that in quadrant 1, we have this graph, and there's a mirror image of that over the origin. In quadrant 2, there's nothing. In quadrant 4, there's nothing. That's a mirror image. So this particular graph does have origin symmetry, and we can say that it is an odd function. Thank you for checking out my videos. Have a great day.